My name is Mihaela Ștefan. I am a professional services engineer at InfiNet Wireless. Thank you very much for taking the time to join our webinar. Today we are going to discuss about the switching configuration options that are available for the R5000 series units. First, we will review the Ethernet frame structure. Then we will check in detail the switch group configuration, and in the end, I will show you what are the best practices for managing the units and how to correctly implement them. Let's begin with the description of the Ethernet frame encapsulation, which will provide us a better understanding of the actual switching process. Each Ethernet frame begins with an Ethernet header, which contains the destination and source MAC addresses, plus a couple of protocol-specific information. The frame ends with a frame check sequence, which is a 32-bit cyclic redundancy check code used to detect the errors that might occur during the data transmission. Next, if you are using VLANs, the Ethernet header will also include an 802.1q tag or an 802.1ad tag for double encapsulation or Q-in-Q. The 802.1q tag is a 4-octet field, and the first two octets are called the tag protocol identifier, in our case 8100. The last two octets include the VLAN ID and the 802.1p priority, to which you are already familiar. Moving forward, additional protocols will add their own header. Therefore, in the Ethernet frame, we will also find an IP header containing the source and destination IP addresses and other specific information. Last, we have the TCP/UDP header containing the source and destination communication ports, as well as protocol-specific information. We are left with the middle section of the frame, which is the data payload, representing the actual data that we want to send over the transmission channel. Let's now check how the MINT protocol comes into play. We can see in the picture a network comprised of two Ethernet segments that are separated by a MINT area. Our R5000 series units use the MINT protocol for transmitting the data, and MINT will add its own header in order to create a MINT frame. Consider, for example, a standard Ethernet frame incoming to the Ethernet interface of master 1. In case of using the polling software version, the entire Ethernet frame, no matter its size, will be encapsulated into a MINT frame using an additional MINT header. When exiting the MINT area, the frame is decapsulated back to the original Ethernet frame and switched from the RF interface to the Ethernet interface of slave 1. Let's quickly check what is different in the TDMA firmware version. We know that the TDMA frame has a fixed duration, while the Ethernet frames have variable sizes. Since we cannot afford to send empty TDMA frames, the solution is to split the Ethernet frames into time chunks with byte resolution in order to fill the entire TDMA frame. We obtain this way a fixed size TDMA frame for transmission. Let's now briefly review some of the MINT protocol principles of operation. First, you should be aware that MINT is a proprietary protocol that encompasses several technologies, and it is only used by the InfiLink 2x2 and InfiMAN 2x2 product families. MINT operates between the data link and network layers of the TCP/IP stack. When switching mode is enabled, the Ethernet frames arriving from the external network are first processed by the switching module of the unit, who will switch them from the external Ethernet interface to an internal MINT interface, more precisely to RF or to PRF. From now on, MINT encapsulates each Ethernet frame by adding its own layer 2 header, as we previously discussed. MINT also strips everything that it considers unnecessary from the Ethernet frame by using the packet header suppression feature, through which all the protocol headers are compressed. Additionally, Mint packs smaller frames to bigger superframes using the burst feature and optionally will perform encryption. Another important aspect is that Mint routes the frames hop by hop, similar to a routing protocol, meaning that each unit will take its own decision. One of the differences compared to a layer 3 routing protocol is that Mint routes the frames based on the destination MAC address and not based on the IP address, like a classical routing protocol. You should also bear in mind that Mint takes into account the link quality in real time and updates the cost for each destination, so it is best suited for wireless connections. Additionally, Mint is loop-free since there is no broadcast inside the Mint area. Even external Ethernet broadcast frames are efficiently sent as one copy for each Mint unit, using multicast groups or unicast according to your specific setup. An important concept we've been talking about is the Mint area, through which only Mint encapsulated frames will pass. We can see in the picture 3 Mint areas separated by an Ethernet segment, which is comprised of the switch connection with the 3 base stations. I will now show you how are the frames actually exchanged between the 2 PCs that are connected to our units. Assuming that the ARP process already took place and the PC1 learned the MAC address of PC2, the first step is for PC1 to send an Ethernet frame for PC2 through its Ethernet interface. The frame reaches CPE3_1, which switches it from Ethernet to RF, entering Mint area 3. Let's see what Mint will do with the frame in order to send it forward. First of all, we need to know that Mint maintains on each unit a table with all its neighbors in the same Mint area and with the cost to reach each of them. Therefore, CPE3_1 will look for the MAC address of PC2 and what is the shortest path to reach it. Next, it will encapsulate the frame into a Mint frame using as destination MAC address, the MAC address of the RF interface on base station 3. Next, the frame is sent through the RF interface. Base station 3 will decapsulate the Mint frame back into the Ethernet frame and switch it towards its Ethernet interface, since we are now exiting Mint area 3. The switch performs classic Ethernet switching and our frame arrives to base station 1. Now the frame will enter Mint area 1 and base station 1 will also look into its own table, decide to route the frame through RF and encapsulate it with the Mint header. Let's remember that Mint also performs additional processing, like for example, protocol header compression. Once the Mint frame reaches CPE1_1, it will be decapsulated into the original Ethernet frame and sent to its destination, which is CPE2. Let's now check the switching configuration details. InfiNet Wireless uses the proprietary concept of switch groups for filtering and for switching layer 2 frames. The Mint network can be viewed as one virtual distributed layer 3 switch, where the border nodes act as the external ports of the virtual switch. Switch groups should be created only on the nodes where the frames are entering from and leaving to the external network. And we mean, of course, the external network related to the Mint network, so the Ethernet network. To sum up, no switch groups should be configured on internal intermediary Mint nodes. Switch groups can be used to transport different types of traffic, like for example, VLANs, IP and MAC addresses, traffic with the same values for the QoS header fields, multicast traffic, and different other common criteria. Next, each group has a unique numeric identifier. Another important aspect is that each node can have several switch groups and the same interface can be used in several groups simultaneously. Let's look at an example to better understand the concepts we have been talking about. Wireless links are established between the units in a point-to-multipoint topology, and all the units are part of a single MINT area. We will reveal the switching capabilities of the units by defining switch groups only for the data traffic. PC4 should be able to communicate only with PC1 and PC2 only with PC3. In order to connect PC4 and PC1, we will create switch group 3 on the base station and on CPE1. Further, in order to connect PC2 and PC3, switch group 4 is added on CPE2 and on CPE3. Since the switch group IDs are different, PC1 cannot communicate with either PC2 or PC3, for example, as expected. Since the communication is possible only between the units having the same switch group ID, let's add the additional switch group 5 on the base station and on CPE2 in order to enable the communication between PC4 and PC2. Let's now see if it's enough to work. We need to know that switch groups are being processed sequentially, starting with the first one in the list. Also, by default, there is no filtering criteria applied to newly created switch groups. Therefore, in our example, all the traffic coming from PC4 to the base station will be put into switch group 3 and switched through wireless. This happens because switch group 3 is the first one in the list, and it has no filtering rules added. The same way, all the traffic coming from PC2 to CPE2 will be put into switch group 4, since there is no filtering rule as well. You can see that no traffic is put into switch group 5, and there is no communication between PC4 and PC2. In order to make this communication possible, we need to create rules for our switch groups, and we will check the configuration options in the next slide. The max switch section in the web interface allows you to configure a multitude of parameters related to layer 2 switching. First, you have the option to enable or to disable the switching module. In the default configuration, switch group 1 is already created, and it includes the Ethernet and RF interfaces with no additional rules. In this case, all the frames incoming to the unit from the local Ethernet interface will be added to switch group 1 and delivered through RF to the opposite side of the link. This simple configuration will enable transparent switching, meaning that all the frames will pass through the link unchanged. For example, all the VLAN tags or QoS fields will have their values preserved. Next, we have the interfaces section that allows you to add new interfaces to the switch group, having one of the statuses. Pass for transparent mode, where the frames remain unchanged. Tag when all packets need to be tagged with a specific VLAN ID. Strip in order to remove the VLAN tags from all frames. Next, we have the options section. Here you can enable or disable protocols like STP or IGMP snooping, and configure some additional operational modes. For example, if the repeater mode is enabled, the unit will act as a hub by simply sending the frames to all the devices' interfaces, except the one from which the frame was received. Let's also check the flood option. By default, our units have a special filter criteria for unicast flood protection. If you will enable the flood option, the unicast flood protection is disabled, and this is not recommended unless some special tests need to be performed. We'll briefly review the modes of the switch. Normal is the default mode, and it means that the switch group operation is based entirely on the configured rules. Trunk and in-trunk modes allow you to simplify the configuration when multiple VLANs need to pass through the base station. For the trunk mode, for example, the frames received through the Ethernet interface are placed automatically in a switch group having a number that corresponds to the packet's VLAN ID. Last, we have the upstream and downstream modes, which offer you a simple choice to avoid multicast terms in very simple topologies by sending the traffic in only one direction, either upstream or downstream. Next, we have the rules section. The rules are used to filter the frames received from the Ethernet interface to a specific switch group, and the frames must satisfy the switch group rules in order to be assigned to it. Afterwards, the switching module will decide whether the packet has to be sent through one of the interfaces or if it has to be discarded. The rules consist of a pcap expression, like we can see in the picture VLAN 100, and the decision to deny or to permit the matching frames. Each frame is checked sequentially against each rule until a match is found. In case that a frame does not match any rule, the default decision for the group or for the interface is taken. Last, we review the ordering options. Switch groups, as we already know, are processed sequentially, starting with the first one. You can change the sequence using the up and down arrows that you can see in the top right corner. Let's now check how can we extend the MINT area to include also wired connections. In the picture, we have three distinct MINT areas separated by Ethernet segments. The Ethernet frames will be encapsulated and decapsulated several times by each MINT area until reaching the peer PC. If we wish, for example, to join MINT area 3 with MINT area 2, we can do this by creating pseudo radio interfaces on base station 3 and on base station 2. The PRF interfaces are considered MINT interfaces, and by joining them in the RF link section, we extend the MINT area through the Ethernet segment as well. We have now obtained a single MINT area between CPE2 and CPE3. In this configuration, the frames coming from PC3 to PC2 will only be encapsulated once by MINT at CPE3 and decapsulated once at CPE2 into the original Ethernet frame. So we have no more several MINT encapsulation and decapsulations. The last topic we are going to cover is the management configuration. In the default configuration, the customer traffic and the remote management are transferred in the same switch group, more precisely switch group 1. It is recommended, although, to separate the customer traffic and the management traffic by creating at least two switch groups, one for the data traffic, another for the management. Let's review the VLAN-based management using VLAN 100 for the management traffic in our example. First, you should create switch group 100 for the management. Afterwards, you should create a VLAN interface in the network settings section, and you should specify the VLAN ID and select the Ethernet interface as its parent. Next, add the RF and VLAN interfaces into switch group 100. In our case, the slave unit is managed via the PC connected to the master unit, so there is no need to add the Ethernet interface to its switch group, only RF should be added. The next step is to attach the SVI interface to the management switch group and to configure it. The management IP address should be added to the SVI interface. So please carefully review the configuration method for VLAN-based management access that I just presented, since it is in use starting with the polling-based firmware version 19033 or TDMA-based firmware version 217. In the end, I want to share with you some useful updates. We are glad to announce that InfiNet Wireless opened official training centers in Bucharest, Dubai, Bogota, and Paris. A training schedule already exists, and you can register to the upcoming events from the InfiNet Wireless Academy portal. The second good news is that a new online tool named Configuration Generator was launched, and it is available in the InfiNet Wireless Academy portal as well. By drawing a network scheme and specifying some general parameters, the tool will generate the configuration file for you. The user does not need to know, in this case, the InfiNet Wireless proprietary protocols and the device's configuration features, which allows to reduce the network deployment time and simplify the process of project implementation. This brings us to the end of today's presentation. Now, if you have any questions, please feel free to write them down in the chat section, and I will answer them one by one. We will just have a short break in the meantime. Thank you. Hello again. We have a question from Nick, who is asking us if there are some examples on the wiki pages. Alexander already sent you some references. I recommend you to look into the InfiNet Wireless Academy, to log in to InfiNet Wireless Academy, and there you will find a lot of documentation with more specific details if you want to learn in detail the protocols. Also, you can access the wiki from our official website, and there should be several documents on the subject. This was a general presentation to show you some capabilities of our units regarding switching. And of course, like Alexander said, if you need some specific scenario and you have some specific questions regarding your own configuration, you can send us an email to support to us, and we will answer your questions. We have another question. What is the main difference between switch group and VLAN configuration if the final purpose is separating the traffic? You must understand that switch groups are more complex, and they can filter traffic based on multiple criteria, not only VLANs. And they are used by our switching module to send the external Ethernet frames to the MINT module for further processing. So you can obtain separation per VLAN. If you are using only one VLAN, and only one rule for VLAN, it's the same separation. But if you need to consider other criteria like IP addresses, TCP ports, priorities, you will need to add the more complex filtering criteria. Also, if you want to have several VLANs passing through a switch group, this is possible. So you can have a switch group to filter a range of VLANs. Nick is saying that switch groups are better. Yes, they are better. They are more specialized, and they do a lot of things, and they are mandatory for our units. Of course, if you want, you can disable switching. And if you disable switching, you will have no switch groups, and you can use routing protocols in the classic manner. But you will still have MINT, who will perform other tasks related to the radio link and encapsulation. But it will not route the packets. So if you disable the switching module, MINT will still be available, but it will not route the packet. It will just perform a packet header suppression. It will assess the quality of the links and update in real time the quality. You shouldn't think about switch groups as an advanced VLAN concept. Switch group is a broader concept. It's not related just to VLANs. Let's say you have an incoming Ethernet frame, and you want some frames to be sent to one destination, some frames to be dropped. Maybe you want to drop some frames, maybe you want to change some priorities in the header. This is possible. Maybe you want to change DSCP values, maybe you want to tag or retag the frames. So switch groups are good for filtering and for modifying the frame structure as needed. Like Bogdan is saying, you can consider that a switch group is a switch that allows communication only between the devices that are connected to this switch. So only the devices that are connected to the same switch group can communicate. If you, let's say, you ignore the MINT topology, you can think of the MINT area as a distributed switch, which has several ports and allows communication between the devices that are connected to it. Okay, I don't see any more questions. For any other clarifications, you can contact us or the support team, and we will answer you specifically. Thank you once again, and I hope to see you in our next webinar as well. Have a nice day.